Kestrel's security team spent the last episode closing a real, embarrassing hole. An API gateway that trusted the shape of a request but never checked whether the caller actually owned the record it was asking for. Rate limiting went in. Schema validation went in. The broken object-level authorization that let one clinician's token page through another patient's billing history got fixed at the gateway, request by request. It was good work, and it closed a real path. Then someone on the team asked the question that actually matters here. None of that touches what happens if an attacker gets code running inside one of our containers anyway. Say, through a vulnerable dependency nobody's patched yet, not through the API at all. And the honest answer was, they'd have no idea. Every control up to this point watches the network, or watches the request. Nothing was watching the one place an attacker who gets past everything above it actually has to act. Inside the kernel, on the machine actually running the workload. Every layer this arc has covered so far, the mesh, the policy engine, microsegmentation, the SASE edge, the gateway, sits above the operating system. Each one inspects a network packet or an application request and makes a trust decision based on what it can see at that layer. eBPF operates somewhere none of them can reach, inside the Linux kernel itself, at the exact point where a system call, a network packet, or a process action actually happens. eBPF stands for Extended Berkeley Packet Filter, and the name is a historical artifact. The original BPF was a narrow mechanism for filtering packets efficiently. The thing tools like TCP dump were built on. What makes it extended is that the kernel maintainers turned that narrow filtering mechanism into a general-purpose way to run small, sandboxed programs inside the kernel, attached to specific hook points, a system call being made, a network packet arriving on an interface, a function inside the kernel itself being entered. Attach a program to the right hook, and you can observe, in some cases act on, exactly what's happening at that point in real time for every process on the machine. The sandboxed part is what makes this safe to run in production at all. Before an eBPF program is allowed to load, the kernel's verifier walks every possible path through it and rejects anything that could crash the kernel, loop without bound, or read memory it has no business reading. Once verified, the program is JIT-compiled to native machine code, so it runs at close to full kernel speed rather than being interpreted line by line. And critically, none of this requires writing a traditional kernel module, recompiling the kernel, or rebooting the machine to load a new probe. That combination, safety, speed, and being loadable at runtime, without touching the workload it's watching, is exactly why eBPF has become the mechanism underneath most of the modern observability and security tooling built in the last several years. This episode's two tools included. Cilium is the first of two real, widely deployed projects built on top of that mechanism, and it started life-solving a networking problem before its security angle became the more interesting story for this episode. It's a CNCF project used as the networking layer, the CNI, for a large share of production Kubernetes clusters, and everything it does runs through eBPF programs attached to the kernel's networking hooks, rather than through the traditional iptables rule chains most clusters relied on before it. The angle worth focusing on here isn't faster networking. It's what that kernel-level vantage point makes possible for security specifically. Traditional network policy is written in terms of IP addresses and ports, which is a genuinely weak basis for a trust decision in an environment where pods get created and destroyed constantly, and an IP address can belong to a completely different workload 5 minutes later. Cilium enforces policy based on workload identity instead. Which service a piece of traffic actually came from, verified at the kernel level as the packet is processed, not inferred from an address that might have changed hands. Ask Cilium whether the billing service is allowed to talk to the scheduling service. And the answer is enforced against who the traffic actually is, at line rate before the packet goes anywhere. The other half of what Cilium gives a team like Kestrel's is visibility through a companion tool called Hubble, an actual queryable map of which service talked to which at the request level, built from the same eBPF data the policy engine already has. For a team that spent the last several episodes bolting policy onto a system they'd never fully mapped, that's not a minor feature. It's the first time anyone at Kestrel could answer what talks to what with real observed traffic, instead of an architecture diagram that was already out of date. Cilium answers a network question: who's talking to whom, and should they be allowed to? Falco answers a different one, and it's the one Kestrel's team genuinely didn't have a tool for at all. Once something is already running inside a container, is it behaving the way it's supposed to? Falco is also a CNCF project, originally built inside SysDig and later donated to the foundation, and it uses the same eBPF mechanism to watch system calls in real time on every container on the machine and compare what it sees against a set of rules describing normal versus suspicious behavior. The rules read almost like plain English once you've seen a few. A shell process spawned inside a container that has no legitimate reason to ever run an interactive shell. A process reading a credentials file it has no business touching. A write to a directory where executable binaries live, coming from a process that isn't part of the deployment pipeline. Falco ships with a substantial default rule set covering exactly this kind of behavior, and a team can layer rules specific to its own workloads on top of it. What makes this a fundamentally different category of detection from anything Kestrel had before is where the observation actually happens. A log-based detection tool depends on the application writing an honest log entry about its own behavior, and an attacker who's compromised that application can simply not do that, or write an entry that lies. A syscall observed through eBPF isn't something the compromised process gets a vote on. If a shell actually gets spawned inside that container, the kernel sees the exec system call happen, whether or not the application ever intended to tell anyone about it. That's the entire value proposition in one sentence. Falco watches the one place a compromised workload can't successfully hide from. Here's the shape of the incident that actually convinced Kestrel this layer was worth running in production, not just worth having a slide about. A background reporting service, not the billing service this arc keeps returning to. A smaller internal tool that generates monthly utilization reports. Pulled in an open-source templating library with a known unpatched deserialization flaw. Exactly the kind of dependency risk this season comes back to properly once we reach the supply chain arc. An external scan found the flaw before Kestrel's own team did, and an attacker used it to get remote code execution inside that service's container. Nothing upstream of the kernel was positioned to notice. The service mesh saw a normal, mutually authenticated connection between two internal services. The request that delivered the exploit looked exactly like the reporting service's usual traffic. The API gateway wasn't even in the request path, since this wasn't an external API call at all. Cilium's network policy allowed the connection because it genuinely was traffic the reporting service was supposed to receive. Every layer built so far did exactly its job, correctly, and the attacker still ended up with code execution inside a running container. What actually caught it was Falco's default rule for a terminal shell spawned inside a container, one of the plainest rules in its base rule set. The exploited process, once it had code execution, did what a large share of real intrusions do next. It spawned a shell to explore the file system and look for a path to something more valuable. Falco's eBPF probe saw that exec system call the instant it happened, matched it against a rule that container image almost never legitimately triggers, and fired an alert in real time. Process name, container ID, the full command line, all before the attacker had done anything beyond opening that first shell. Kestrel's on-call engineer had the container isolated within minutes of the alert, not the roughly 6 weeks. The original billing breach ran undetected. Nothing in the reporting service's own logs would ever have shown this, because the compromised process had no reason to log anything true about what it had just done. Step back from the specific incident, and the architectural point is the one this whole season keeps returning to, just pushed one layer deeper than before. Assume breach, as a mindset, says, don't design as though your upstream controls are perfect. Design for what happens after one of them fails anyway. Every earlier episode in this arc applied that at the network or the request layer, mesh identity, policy decisions, segmentation, the gateway. All of those still assume the attacker is trying to get in. eBPF-based runtime observability is what assume breach looks like once the attacker is already, actually, inside. Code, executing on a real machine, inside a real container, regardless of which upstream control they got past or exploited to get there. That's also why this layer earns a genuinely different level of trust than log-based detection, and it's worth being precise about why, rather than just asserting it. A log is something the observed system chooses to produce. A syscall is something the kernel observes directly, as a fact about what actually executed, with no dependency on the observed process's cooperation or honesty. An attacker with code execution inside a container can disable an application's own logging or falsify it without much difficulty. Disabling the eBPF probe, watching that container from the kernel, is a fundamentally harder problem, because it isn't running as part of the thing being observed. It's running underneath it, watching from a vantage point the compromised process doesn't control. None of that makes this a replacement for anything earlier in the arc. It's a genuinely different question, asked at a genuinely different layer, and it's the layer that answers the one none of the others can. If everything above this failed, and eventually, for something, it will, did anyone actually notice, and how fast? A few mistakes recur often enough to be worth naming directly. The first is treating Falco as a box to tick, rather than a rule set that needs tuning against your own workloads. The default rules are a genuinely strong starting point, catching exactly the kind of behavior this episode's worked example relied on. But a team that never adds rules specific to its own applications will eventually either miss something particular to how their systems actually run or drown in false positives from generic rules firing on legitimate, unusual-looking behavior. The second is deploying this kind of tooling and routing every alert into a channel nobody actually watches in real time. Runtime detection only pays for itself if there's a real response process behind it. The same on-call discipline that let Kestrel isolate the reporting service within minutes instead of weeks. A detection layer with no response process attached to it is expensive observability, not security. The third is assuming Cilium's network policy enforcement and Falco's runtime detection are interchangeable, or that having one makes the other optional. They watch different things. One enforces who's allowed to talk to whom at the kernel level. The other watches what a process actually does once it's running. And Kestrel's incident is a fairly clean illustration of why you'd want both. The network layer correctly allowed a connection, It had no way of knowing was carrying an exploit, and the runtime layer is what caught what happened after that exploit landed. Every episode in this arc, this one included, has been about enforcing or observing trust at some point after a request or a process is already underway. The mesh, policy, segmentation, the gateway, now the kernel itself. There's a question sitting underneath every one of those mechanisms that we've mostly assumed the answer to so far. When a system actually checks whether a request is allowed, what model is it checking against in the first place? Roles, attributes, relationships between specific pieces of data? That choice is its own architecture decision with its own scaling failure modes, and it's next. That's authorization patterns, RBAC, ABACE, and rebase, including the relationship-based model Google built at planet scale as Zanzibar. Next episode. If you're building systems that need to notice what happens after every other control has already failed, subscribe, and I'll see you in the next one.